Okay, hello. This is Patrick O'Shaughnessy. I'm a professor at the University of Iowa. Developed a series of modules to primarily to focus on the needs of a master's student or PhD level student who is acquiring data in the lab or the field and then needs to understand the variety of different data displays and data analysis techniques all the way up through some sophisticated statistical techniques that might be appropriate for your data. And so with that in mind, we'll get started with this module on graphing techniques. Here we're showing a module map of the first 5 modules in this series. See, we're going to start with graphing techniques and then move into regression analysis. Which is somewhat tied into graphing because you often have a XY plot done before you're going to do a regression analysis itself. So I'll explain these as we move along. So first of all, you need to know that the software package that has been chosen for this particular module and all subsequent modules is readily available, which is Microsoft Excel. However, to take fully advantage of the methods in Excel, you need to first load in or add in what's called the data analysis tool pack. So you can see here that you first need to go up in the top ribbon and click on File. Then you'll see down at the bottom left Options, and then focus in on the add-ins right down in this area right here. And then ultimately you're going to hit a Go button down at the very bottom of the screen that had popped up. And when that happens, you'll see an add-ins box that shows up, and you can click on the analysis tool pack there, hit OK, and you're going to have it loaded in. Then the question is, where is it loaded in? You'll then go back out into Excel and go to the Data ribbon, or the data on the ribbon, and over on the far right you'll see data analysis. So that will give you a large set of the statistical software options within Excel. So you can see here when clicking on the data analysis, it opens a window and these are the different operations available. I had to give 2 screenshots of them, but you'll see they go down from ANOVA, correlation, covariance, descriptive statistics, even Fourier analysis, histograms, moving average, rank and percentile, regression, sampling, and a variety of different t-tests. So all these will be available to you now once you pull in that data analysis tool pack. So moving forward now, we're going to just look at different ways of displaying your data. This is something that's going to have to happen ultimately in some report or maybe a thesis, dissertation that you're going to write. You're going to have to encapsulate the data you have obtained in table form and or graphical, and we're going to look at the graphical displays now. So for example, you have a variety of different data. In this case, there are some sort of a device you have that allows you to collect measurements kind of on the fly. These are quote-unquote real-time measurements resulting from a direct reading instrument, of which there are many available. And you can see here that each one of those little squiggles represents a point that was a sample taken by the instrument. So in this case, many different, perhaps every second, because the x-axis scale is minutes. Over here, the x-axis scale is days, so they also look like little squiggles, but in this case, they're probably maybe every 5 minutes over a day rather than every minute or even half a minute on the left. You can see in general, you're getting across an idea, a visual description that a viewer can see. Oh, on the left, there was some sort of a reason for a downturn, and then a slow, steady increase, and maybe what you're going to describe as some sort of a plateau or a steadying level of your measurements over time. Whereas, of course, on the right, there is some reason for some rather drastic upward and downward trends, not completely consistent, but you might say that there's some sort of diurnal variation going on, for example, as part of the quote-unquote story that you are trying to state to your viewers of the graph. Note that each graph will have an x-axis labels, and the units will be placed there next to the title for the x-axis and for the y-axis, so those are necessary. There's a simple box around the entire graph. These are done in Excel as well. There's many different options that we can get into, but this would be a typical approach here. Okay, now here's another type of graph that is used quite a bit in XY relationship. In this case, someone has done an experiment in which the speed of a pump has been varied from some number to some number, and the output rate, maybe so many gallons per minute, has been measured. And actually there's two pumps here, so they show, of course, that there's a linear relationship between speed and output rate, which might be the point. Now the graph itself, are the options here, of which there are many in Excel, are they necessary? Do they get the point across, or could changes be made? Right off the bat, we see that the titles do not have units associated with them, so that's a problem that needs to be fixed. So speed, perhaps with a comma, RPM would fix that problem. And then there's other options like the regression lines. They can be dotted, they can be gray. Here they're both the same. Is that okay? They delineate each other quite a bit, so they're far enough apart that might be okay, but maybe making one dotted and one solid would be an appropriate fix here. There is the possibility for minor tick marks. You see the major ones between each of the major axes labels, but maybe minor tick marks would help with some resolution. Now notice the data points are connected by a line. Is that necessary? In this case, the answer would be no. These were done or made as independent measurements, so think of it that way. The speed was adjusted to 60, for example, and then the output rate was measured, then it was adjusted to 70, and the output rate was measured again. There should not be lines connecting those, like there would be if it's a time series in which they are connected by time, as in the previous examples. What about the gray background? Maybe in a PowerPoint, something like that might be okay, or a poster, but typically not in a published article, for example, report, and that sort of thing. Is the upper title necessary? So that is available, but in most cases, again, in a report, you're going to have what's called a figure caption. That will delineate down below what the graph is all about, and therefore the title's not necessary. Is the graph outline necessary? That's the big box around the outside. Again, maybe, maybe not. Most cases, not. And then are the grid lines necessary? So all these questions, just to know that the options exist, and feel free to make adjustments as necessary. For example, here's the exact same data, obviously all cleaned up. There are axes labels now, or the units are there. There's also a legend to delineate between pump 1 and pump 2. The regression lines are different as suggested, and the axes labels have the units. So that would be a far more appropriate graph to put into a final publication, for example. So here's another example of the use of graphics, in this case more on the engineering or physical world side of things, where you have a mathematical model and you want to determine whether or not reality matches it. So for example, here is a classic equation that defines the monotonic increase of anything in a gaseous or liquid media. In this case, in a well-ventilated room, you start off with C0, some concentration, and over time it progresses into some concentration T. So you go ahead and make some measurements associated with that. And so, for example, here's a graph that might be utilized for doing just this, where you have a variety of different measurements made by a direct reading instrument again over time. And then you can demonstrate, the start time of your gas injection and measured gas concentrations and tweak, in this case, the constant K to best match the model to the predicted values. So you can see here there were no lines connecting the individual dots. It would be okay in this situation, as mentioned before, because they are measurements over time. However, when doing so, it made it impossible to see the blue line of the model below it, so that's why they were deleted. Okay, another example, here's the Q equals some constant times the square root of delta P. That is the relationship between the pressure drop, delta P, and the flow rate in a tube Q. So we can go ahead and get our data, measurements of pressure drop and the resulting flow rate in the tube. You can see a really good close association with it. Again, we'll do some regression analysis later on to validate this model approach, but in this case we'd say yes, the model is doing a good job of mimicking reality. You might take this one step further, however, and fit a polynomial equation, in this case a cubic equation. You can see it is extremely accurate in terms of going through the data points. And then the question becomes, well, which is best? And that depends, again, on what your story is. Are you trying to determine whether the data fits the physical model, in which case the left graph would be appropriate? Or are you just trying to figure out, say, some mechanism by which you physically want to determine the flow rate relative to delta P, in which case the right one would actually be the most accurate to use in that kind of calibration between the two factors there. Okay, so that's graphing of different types of the data that you may have measured. What about indicating variability in the data? Well, for that you need multiple measurements of the same thing. Typically, you keep your system at a certain setting and you measure it once, measure it again, measure it again. So here's an example where we have 5 different samples and someone actually measured each one of these things, whatever they are, 20 times. So you have what are called 20 observations for the 5 samples of reality. Maybe these are heights of corn plants out in 5 different fields, for example, or chemical measurements in 5 different ponds, whatever. So of course you can use the Excel function average to determine the average, and you can use the Excel function of standard deviation to determine their standard deviation. Now what you're actually doing is graphing just those values down here. You're not graphing all of the sample values themselves, because that's not important. So here are 2 examples, one where a point is indicated for the average, and then the error bars, which are created in Excel, it's an option in the graph to indicate the variability in terms of a standard deviation. Or exactly the same values are given in a plot, a chart, so to speak here, a box plot, a chart plot, where again the error bars can be added to them. So these are the same thing, just 2 different graphing techniques for indicating data variability of a variety of different data sets you have. Speaking of box plots, so this is what they look like. You can see, yes, they are a variety of boxes in this case, where there's a main box with a line in the middle, as you can see, and then these kind of whiskers, as they're called, that extend above and below, really give a better idea, in a sense, of the distribution of the measurements that you have obtained. And what do they mean? Well, a little asterisk means an outlier. It's something way outside of what would be typically expressed in terms of the probability of this thing being part of the population of that values. The whisker end is associated with the upper quartile, Q3, and the lower quartile. Again, the math is there, don't worry about it, but it again indicates the extent to which you would expect values to be in for the given their range. So again, here's the third quartile. Q3 is at 75%, so that's what the upper part of the box is. The middle value is typically the median, not the average. And of course, here's the lower quartile. So you have 50%, 75% minus 25 is 50%, all the values are within the box. And then again, you have the smallest values typically within this whisker range here. So that's a box plot, can be done in Excel. Another way of expressing now variability is not in terms of kind of the range of measurements, but in terms of their distribution. How do they spread themselves relative to an average value, for example? Or how are they spread out? So that's where we get into the idea of a histogram, where, as you can see here, let's say we have 20 data values, and we want to know how they are distributed across the range of their measurement value, whatever it happens to be. Let's just say these are meters, for example. So we can go now to one of the uses of the data analysis tool pack, which has a histogram option, which does the hard work of collecting all the values, the number of values within a certain range. For example, there are no values between 11.5 and 11, so it gives it a 0. Between 12 and 11.5, there is a value, so that's given a value of 1, etc. So that puts the number, the frequency associated with the bins for you automatically. Again, it's hard to do by hand, so to speak, in Excel. Now you can create a bar chart, in this case a clustered bar chart as it's called, which indicates the frequency of values within those ranges. And so this is now a histogram, and it gives you an idea of how, again, the values are distributed. In this case, between about 12 and 15.